Let's talk about rotation equations. The first one we want to talk about is the definition of the radian. Theta is equal to the arc length divided by the radius. And that's theta in radians. So the angular position or angular displacement is equal to the arc length divided by the radius. What that means is, so here's the radius, and if I go around this arc length here, then this is theta here. If the arc length is equal to the radius, then theta is 1 radian. And so that's how you define the radian. So theta equals a linear distance and arc length over r. Omega, the angular velocity, is equal to v over r. Alpha, angular acceleration, is equal to a over r. And we can take these equations and we can relate them back the other way. So linear distance or displacement is equal to r theta. Linear velocity is r omega. Linear acceleration is r alpha. And there we go. So those are our basic equations that we have to start out with for rotation. With those equations, we can look at our kinematics equations that we had. So for example, if you remember, we'll say the linear or the translational here and the rotational here, the equations are all the same. It's a beautiful thing. All the rotational equations are pretty much the same equation as the linear, the translational ones, just with some Greek letters instead of English. So in the linear, where we had d equals vt, in the rotational we simply translate the English into Greek here. So what we have is angular displacement theta equals angular velocity omega times t. That's our constant velocity equation. Where we had v equals v naught plus at for translational, rotational looks like omega equals omega naught plus alpha t. Remember this one, d equals v naught t plus 1/2 at squared? Well, it's going to look like this. Theta equals omega naught t plus 1/2 alpha t squared. d equals v plus v naught over 2 times t. Theta equals omega plus omega naught over 2 times t. And then v squared equals v naught squared plus 2ad looks like omega squared equals omega naught squared plus 2 alpha theta. So there we have our rotational equation. You can see they're pretty much the same as the linear ones. They just have the rotational variables, the Greek variables instead. And the same is true for other aspects of rotation. So after kinematics, if we look at Newton's laws of dynamics, for example, dynamics, Newton's laws, where we had the translational net force equals mass times acceleration, we have for rotation, similar idea. Instead of force, we have torque. The net torque equals, instead of mass, we have the rotational inertia, and instead of a, linear acceleration, we have alpha, the angular acceleration. So torque equals I alpha. Now, let's talk about torque for a second. Torque is equal to r perpendicular times f, or rf sine theta, or r cross f. Those are different ways of finding the torque acting on an object. So r perpendicular f basically means I take the perpendicular component of the force multiplied by the radius, and I've got it. So that's how I do it. So for example, the example I always like to use is a wrench. So here I got this wrench. If I apply a force right here at this point, then here's my axis of rotation. My r is the distance from the axis of rotation to the point the force is applied. The force here that's applied in this direction, there's an angle theta here between the r vector and the f vector, and that angle theta, I simply take r times f times the sine of theta. That will give me the torque. Or I take the component of force that is perpendicular to the radius and multiply that. Or I could take the perpendicular distance from the axis of rotation to the line of action, in this case extending that line of force, and that would give me the torque as well. So those are some different ways of finding the torque, an individual torque that's acting on an object. Inertia. We need to talk about that for a second. Inertia is defined as the sum of m times r squared. So for particles, I simply take mr squared for each particle and add them together. R is the distance from the axis of rotation to the location of the particle. Now, sometimes we don't have particles, we have an extended object. And so for that, we did learn a few of these. Well, let's look at the basic formula here. It becomes the integral of r squared dm. And without getting into too much detail, I did create a video on the moment of inertia, or the rotational inertia integral, and I'd encourage you to watch that one if you'd like to get a little more specific on how this integral works. But we learned a few of these shapes. So we had a cylinder with an axis passing through the center, and that one is 1/2 mr squared, with a cylinder of mass m and radius r. We had a solid sphere, so yeah, not a very good drawing of a sphere there, but trying to make it look like a sphere. So the inertia of a sphere, axis passing through the center, uniform solid sphere, is 2/5 mr squared. Then we learned one for the ring. Okay, uniform ring, or a hoop, I'll call it a hoop. And because all of the mass is equidistant, this is just mr squared. We also learned a uniform thin rod, an axis passing through the middle is 1/12 ml squared, L being the length of the rod. And then we also had the same rod, but with an axis passing through the end, was 1/3 ml squared. So those were some inertias of some common solid shapes that we wanted to make sure that we remembered. And along those lines, we also learned the parallel axis theorem. And the parallel axis theorem basically says that the inertia of an axis that is parallel to an axis passing through the center of mass, for which I know the inertia, can be found by taking this center of mass inertia and adding to that mh squared. Now in this formula, h is the distance from the center of mass to the axis of rotation. So just as a quick example, if I take my rod through the end, right, I know that an axis passing through the middle has an inertia of 1/12 ml squared, and through the end is 1/3 ml squared. That's what we decided. We learned those. But let's just see how it works here. So here I have an axis that is parallel to this one that passes through the center of mass. So I can find the inertia of this axis, right? The end is equal to the center of mass inertia, 1/12 ml squared, plus m times h squared. Now h is distance from center of mass to axis of rotation. So if it's here, that is L/2, half the length. So I do L/2 squared. That becomes then 1/12 ml squared plus 1/4 ml squared. And a 12th plus a 4th, get a common denominator. That's 3/12, 1/12, that's 4/12, which is in fact 1/3. And so the parallel axis theorem verifies that the inertia of an axis passing through the end of the rod is in fact equal to 1/3 ml squared. That's kind of how you use the parallel axis theorem. So next up on our tour of rotational equations is angular momentum. Angular momentum, the symbol we use is L, and angular momentum is equal to I omega. Just like linear momentum, remember, P was mv, so in place of linear momentum we have angular momentum, in place of mass we have inertia, in place of linear velocity we have angular velocity. So this is again just a direct translation from linear to rotational, or from English to Greek, as I like to say sometimes. Now there's another way to find angular momentum, and that is r perpendicular times mv, or in other words r cross p, cross product of a position vector with a momentum vector. So r perpendicular mv, or of course that means r mv sine theta, where theta is the angle between the r vector and the v vector as well. So those are some ways to find angular momentum. Now, the net torque is equal to dl dt, the rate of change of angular momentum, which implies that if the net torque is 0, then angular momentum is conserved, just as we saw served. Just as we saw with linear momentum, that when the net force is 0, linear momentum is conserved. So if the net torque is 0, then angular momentum is conserved. That means that L initial is equal to L final. A good place to see this is an elliptical orbit problem with, say I've got some kind of a spacecraft or a planet or something orbiting the sun here. And so this is R1 and this is R2, angular momentum, because the only force acting on the satellite is the force of gravity, and it's passing through the center of rotation there, then there is no net torque. That force of gravity produces no torque, and therefore angular momentum is conserved. So I could say R1 mv1 equals R2 mv2. The mass would cancel out, and depending on what information I had, I could solve it that way. But it works great for elliptical orbits. That's not the only application, but that's just one application of angular momentum conservation. And one last equation here in rotation is rotational kinetic energy. If something is rotating, a solid object is rotating, then the individual particles of that object are in fact moving. Energy. There we go. And we call this K rotation. K rotation is simply 1/2 I omega squared. It looks very similar to the translational 1/2 mv squared, right? But an object can have rotational kinetic energy if it's rotating. So the classic problem of, here this is a height h, I've got an object here that's going to roll down the hill, and I want to know how fast is it moving at the bottom. I can solve it with energy. So energy initial equals energy final. So what I have is mgh initial equals the final 1/2 mv squared, because it is moving, center of mass there is moving along, plus it is also rotating, so I would have 1/2 I omega squared. Now, depending on what shape it is, will tell me what the inertia is. Let's say it's a cylinder. If it's a cylinder, then the inertia is 1/2 mr squared. So my equation would look like this. mgh equals 1/2 mv squared plus 1/2 I is 1/2 mr squared. And because omega equals v over r, we learned that earlier, omega squared is v squared over r squared. So I'm going to replace omega squared with v squared over r squared. Watch what happens. The r squareds will cancel, and now I have mgh equals 1/2 mv squared plus 1/4 mv squared. So 1/2 plus 1/4, like terms, 3/4. mgh equals 3/4 mv squared. The mass will divide out. The square root of 4/3 gh is my speed. And so anytime you're dealing with rotational kinetic energy, this rotational kinetic energy is just one extra term in the overall conservation of energy equation. And that's how you do it.